Welcome to this lecture. Our today's topic is potential energy of a magnetic dipole or a bar magnet in magnetic field. The magnetic field which we assume here is a uniform magnetic field which comprises of magnetic lines that are straight, parallel and equidistant. So these magnetic lines represent a uniform magnetic field. In this magnetic field, we have placed a bar magnet. A bar magnet, as you understand, is a magnetic dipole. It has a south pole and a north pole. Now, different orientations which this bar magnet can have is that if this is the south pole of magnetic field, if this is the north pole of magnetic field, here the magnetic lines of force terminate, then the south kept towards north, the north kept towards south will be the orientation of this magnetic bar or a dipole, which we will see is a stable orientation. A force acts here on the north pole, attracting it towards south. A force acts here on the south pole, attracting towards north. The field is uniform. These two forces are equal. They cancel out each other because they act along the same line. And I will say that this position of the bar magnet is a position of stable equilibrium. Now the idea of stable equilibrium occurs to us like this. अगर हम gravitational field में इस object को drop करते हैं, like right now there is presence of gravity, तो आप देखेंगे कि ये object जो है, it will fall down to the floor and stay there. Now why did it not go up? Why did it not come and stop mid-air? Reason बड़ा simple. In this room or in this setting, the object acquires minimum potential energy at the floor. Allowed to go beyond the floor, it will keep moving towards Earth's center till the time it acquires minimum potential energy. तो जो minimum potential energy है, वो इसकी stable position बन जाती है. Now whenever I move it from floor upwards towards ceiling, the height with respect to floor increases. इसकी potential energy बढ़ जाती है. इसकी potential energy बढ़ने का मतलब यह है that it is acquiring a position of not stable equilibrium. It will have tendency to go towards the position of stable equilibrium. So let's keep it in mind कि जब हम bar magnet को इस orientation में देखते हैं, this is the orientation where bar magnet will acquire stability. It will be stable equilibrium. The way we have in this room कि position of zero potential energy is the position of stable equilibrium. I will say before we bring mathematics, mathematical expression को लाने से पहले मैं इस position को, so this should be the position of minimum potential energy. और वो potential energy क्या होगी, that we will see. Now you will also agree कि अगर मैं इस orientation को अब ऐसे कर दूँ, suppose I keep this bar magnet in this manner, कि जो इसका north end है bar magnet का, वो north को face करे और जो south end है वो south को face करे. तो आप एग्री करोगे कि मैंने इसको रोटेट किया विद रेस्पेक्ट टू दिस पोजीशन, मैंने इसको रोटेट किया थ्रू एन एंगल ऑफ 180 डिग्री. सो आई हैव रोटेटेड इट थ्रू एन एंगल ऑफ 180 डिग्री. और यहाँ पर आप देखोगे कि नॉर्थ रिपेलिंग नॉर्थ, साउथ रिपेलिंग साउथ. सो इसमें अब टेंडेंसी आ जाएगी कि दिस विल नॉट बी अ पोजीशन ऑफ स्टेबिलिटी, ये अनस्टेबल पोजीशन होगी. यू विल आल्सो एग्री कि अगर हम इस बार मैग्नेट को परपेंडिकुलर कर दें मैग्नेटिक फील्ड के, सो दिस इज नाउ साउथ, तो ये जो नॉर्थ है इसको मैंने 90 डिग्री के थ्रू रोटेट किया है, 90 डिग्री के थ्रू. सो दिस इज नॉर्थ, नाउ दिस इज साउथ. आई हैव गिवन इट अ रोटेशन ऑफ 90 डिग्री. तो वहां पर क्या पोटेंशियल एनर्जी होगी वो भी हम देखेंगे. नेक्स्ट इज कि आपको याद होगा दैट व्हेन वी डिस्क्राइब ए मैग्नेटिक डाइपोल और ए बार मैग्नेट, देयर इज अ क्वांटिटी जिसको मैग्नेटिक डाइपोल मोमेंट कहते हैं. व्हाट इज मैग्नेटिक डाइपोल मोमेंट? Magnetic dipole moment is that if this is the magnetic length of a bar magnet called as 2a, then one of the poles has got a pole strength qm. So we define a vector magnetic dipole moment given by 2a multiplied by strength of one of the poles which we assume qm. और अगर इसको आप डायरेक्शन देना चाहते हैं, then this 2a is a vector directed from south to north. So this is directed from south to north. So this is the direction of m vector. Then we have this vector form of the equation. Furthermore, आप यहाँ देखोगे कि in this case जहाँ पर south और north के बीच में ये डायरेक्शन बनती है, the bar magnet has settled down in such a manner कि जो इसका magnetic dipole moment है that is parallel to the magnetic field. So I call this as a position where we named कि इसने एक stable equilibrium acquire किया. You will also see from this diagram कि अगर ये इसका magnetic dipole moment है, here is the magnetic dipole moment directed from south to north. So जब magnetic dipole moment anti-parallel बनता है, which means it is parallel to minus b, or they are opposite in direction. So this would be an unstable position or a position of unstable equilibrium. और उसके बाद एक बीच में और position आ गई where the rotation has occurred to an angle of 90 degree with respect to the direction of b. So this is m here. So here is the m which is directed at an angle of 90 degree with respect to b. तो इस सब information को जो एक physical एक information है, this is what physics tells us, तो हम इसको एक mathematical form में अब डाल देते हैं. The moment I rotate this bar magnet, there is a kind of rotation which is being caused by torque. और जैसे इस पर torque act करना शुरू करता है, जब मैं इसको इस orientation में ले आता हूँ, there will be a force here, there is a force here. So we are trying to fight against that torque. वो torque इसको हमेशा एक इसी पोजीशन में रखना चाहता है where m becomes parallel to the magnetic field. Like कि जब हम एक ऑब्जेक्ट को, जैसे ये ऑब्जेक्ट को जब हम ग्राउंड से लिफ्ट करते हैं, the ground wants to keep it near itself, लेकिन हमारा जो उस पर वर्क है, that work is pulling it up. और आपको याद होगा that in gravitational field, when we pick up this object, we do a work mgh. Now the gravitational dynamics or the force acting there here is different because यहाँ हम rotation की बात करते हैं. Rotational dynamics tells us कि जब भी हम एक torque की presence में object को rotation दे देते हैं, say the rotation is d theta or there is a torque acting on the object, then in the presence of that torque, the work done would be dw, and dw is equal to magnitude of torque multiplied by d theta. D theta is the small rotation which we give to this dipole. In that case, what will be the magnitude of torque? ये हमें already पता है. In the previous lecture we have seen that magnitude of torque is m into b into sine theta, where theta is angle between m and b. Or the vector form of this equation जो हमने already established किया है, that gives m cross b. So in this way we can now write dw equal to mb sine theta into d theta. Now in order to determine work, अगर इसको हमें rotation दी from an initial position theta 1 to a final position theta 2, that work done will be given by this integral. So integration of dw becomes w. On the right hand side we have integration of mb sine theta d theta. So this is from theta 1 to theta 2. Theta 1 is the initial angle and theta 2 is the final angle. अब देखिए इसमें m और b दोनों constants हैं. Because with rotation magnetic dipole moment does not change, then the magnetic field does not change in magnitude. At any position the magnitude of magnetic field remains same. So we have m and b as two constants out of the integral theta 1 theta 2 integration of sine theta with respect to theta. Now this will be further, we have w equal to mb into integration of sine theta is minus cos theta. So this is minus cos theta into, so there is limit theta 2 and theta 1. If I take this minus sign out, so I have minus mb into cos theta, limits are theta 2 and theta 1. Now giving the limits to cos theta, we have minus mb into cos theta 2 minus cos theta 1. Now this is somehow the expression for work done. And this expression if you see very carefully, जब हम एक ऑब्जेक्ट को रेज करते हैं ग्रेविटेशनल फील्ड में from initial position at the surface of ground to a height h, we are actually calculating work done by determining the difference of two potential energies. तो अगर हम देखते हैं कि ग्राउंड पर उसकी पोटेंशियल एनर्जी जीरो थी, at height h its potential energy is mgh, the work done will be mgh minus 0. अगर हम h1 से h2 तक ले जाएं, then the work done will be mgh2 minus mgh1. So I look at this equation. अगर आप इस equation में देखो, this is basically a difference of two potential energies. So if I write that this work done gives us the potential difference actually, so that way we can agree to that कि अगर हम इस equation को potential energy के बराबर लिखें, we have the potential energy equal to we have minus mb into cos theta 2 minus cos theta 1. तो मैं इस इक्वेशन को ऐसे भी लिख सकता हूँ माइनस एम बी कॉस थीटा 2. सो माइनस एम बी कॉस थीटा 2 माइनस इंटू माइनस इज प्लस प्लस एम बी कॉस थीटा 1. नाउ एग्रीइंग टू दिस कि जब हम एक इनिशियल एंगल लेते हैं या इनिशियल पोजीशन लेते हैं, इट बिकम्स द रेफरेंस. इन दिस केस वी प्रेफर टू मेक दिस ए कन्वीनियंट मैथमेटिकल रिलेशन बाय चूजिंग ए रेफरेंस. रेफरेंस के चॉइस से दो पॉइंट्स की पोटेंशियल डिफरेंस या पोटेंशियल एनर्जी की डिफरेंस नहीं बदलती. सो वी कैन चूज द ग्राउंड इनिशियली एज ए पॉइंट एट हाइट h1 फ्रॉम द अर्थ सरफेस, देन द सीलिंग ऑफ ए रूम एट द हाइट h2 फ्रॉम अर्थ सरफेस एंड कैलकुलेट इन ए बिल्डिंग, द पोटेंशियल डिफरेंस विल रिमेन सेम. दैट वे द चॉइस ऑफ आवर ग्राउंड इज आर्बिट्ररी. हम कोई भी चूज कर सकते हैं. फॉर दैट मैटर हम अर्थ के सेंटर को भी एक रेफरेंस पॉइंट मान सकते हैं. सो इन दिस केस व्हाट आई विल डू इज आई विल चूज, सो वी चूज थीटा इक्वल टू थीटा 1 इक्वल टू 90 डिग्री एज रेफरेंस पॉइंट, एज रेफरेंस. दिस इज फॉर मैथमेटिकल कन्वीनियंस. तो इससे हमें क्या मिलेगा? वी हैव u इक्वल टू माइनस एम एम बी. सो दिस माइनस एम बी, here it is cos theta 2. Now this cos theta 2, I don't need to call it as theta 2 now. I call it as theta. तो ये जो u है, this becomes minus mb cos theta, and I can call it like this कि अगर mb cos theta आप देखोगे, it is dot product of m and b. So I have the relation that potential energy is negative dot product of m and b by choosing the reference theta 1 equal to 90 degree. And theta 1 equal to 90 degree has some importance here कि जब हम theta equal to 0 degree से start करते हैं, this potential energy function ये electrostatics में भी आता है, ये आपको gravitation में मिलेगा, यहाँ भी मिलेगा. तो we have to think of this potential energy function as a scalar quantity. This scalar quantity will have a variation like this कि अगर हम positive, negative और zero values की बात करें, then what happens कि the moment I think of this position, when there is probably north and south along the say magnetic moment जो है, it is along the magnetic line of force. So what will happen in this case? The angle between m is this now. Magnetic dipole moment is m, south to north. The angle between m and b, B, the magnetic line of force, the black line. This m and b are making 0 degree angle with each other. So as per that relation, you will see okay, what happens if theta is equal to 0 degree. So if theta is equal to 0 degree, जो u होगा, it will become minus m b cos 0 degree, right? So that way it will be minus mb. m is positive, b is positive, तो ये एक negative quantity बनती है which gives us its potential energy. Then if I say theta is equal to 90 degree, see what happens. Now u becomes equal to minus mb into cos of 90 degree, that is 0. What happens if theta is equal to 180 degree? we have u equal to minus mb into cos of 180 degree. Cos of 180 degree is minus 1. So minus into minus is plus. So we get plus mb. So from here you will see now that there is a variation. The variation is कि हम plus mb की वैल्यू से जा रहे हैं towards minus mb value. So this plus mb minus mb, this becomes the minimum potential energy which it will have at theta equal to 0 degree. The angle between m and b is 0 degree. This is the stable equilibrium. But we are passing from this minimum value to the maximum value through the value 0. Even though potential energy is a scalar, but it can take the values which are negative and positive. And while you pass from negative value to positive value, this is a continuous function. तो इसमें आपको 0 के थ्रू ही पास करना पड़ेगा. The moment I pass through 0, here is the position. ये जो position आप देख रहे हैं, this you will have to cross. That means starting from theta equal to 0 degree, this is theta equal to 0 degree, going to theta equal to 90 degree. I come from minus mb to 0. Then from 90 degree to 180 degree, this is theta equal to 180 degree. I go from minus mb to 0 to plus mb. This explains our initial point जो से हमने start किया कि अगर हम physically देखें कि एक stable equilibrium minimum potential energy को represent करता है और एक unstable equilibrium maximum potential energy को represent करता है. So in this setup, the dipole has the minimum potential energy when magnetic dipole moment is oriented with P. It has the unstable position when this is anti-parallel to B, magnetic dipole moment, and B are anti-parallel. It acquires maximum potential energy, and here the potential energy is 0. अब इस चीज को लेके I have a justification here कि मैंने उस पोजीशन को जब मैंने थीटा 1 को 90 डिग्री लिया, actually I have taken this as the zero potential energy position. Or with respect to this zero potential energy, if this lies at some angle theta now, or theta 2, or theta, it has a potential energy given by this expression. And this expression, you will see, it agrees with something in electrostatics, जहाँ हमने electrostatics में एक electric dipole की बात की. So electric dipole के लिए U becomes equal to minus P. P is electric dipole moment dot E. So I would desire कि आप इस expression को revisit करें. There will be a lot of symmetry between the two. Now the next thing I have to say is कि एक magnetic dipole जो current loop की शक्ल में भी हो सकता है या एक bar magnet की शक्ल में हो सकता है. For that, this dynamics remains same. The scalar nature of U makes it directionless. Then you can think about its unit. Its unit will be same as that of work. We have acquired it from work, so its unit will be joule. And for the purpose of practical applications, this concept becomes very significant. We find that Earth, which is a sphere with some molten lava inside it, has circulating currents. It behaves like a magnetic dipole, and that magnetic dipole in the state of rotation has a dipole moment. Then an electron moving in the atom, then different particles, most of the subatomic particles like proton, including neutron, they have some magnetic dipole moment associated with them, and this expression would remain true provided they are in the uniform magnetic field. Now finally, I would like to determine that how much would be work required to be done if we make a dipole, magnetic dipole, to pass from this position where M is anti-parallel to B to the position where M is parallel to B. तो इसका तरीका ये होगा कि this would be the difference of potential energy which will be equal to work done, this will be equal to work done, and this work done can be found as U at the value of theta equal to 180 degree minus U at value of theta equal to 0 degree. So this U 180 degree will come from this equation. This is minus MB cos 180 degree minus this is minus MB cos 0 degree. Now you know cos 180 degree is minus 1. So this will be plus MB minus, you know cos 0 degree is plus 1. minus into minus will be plus, plus mb. So this will be twice mb. This will be the work to be done if we have the change of orientation from theta equal to 180 degree to theta equal to 0 degree. You can similarly handle other angles if they are given to you in problem solving. Thank you.